Imagine throwing a ball straight up into the air. As it rises, it slows down. It loses energy. Eventually, it stops, then falls back down. This makes perfect sense. Every object you have ever seen loses speed when it loses energy. A car running out of fuel coasts to a halt. A spinning top gradually winds down. Energy drains away, and motion fades with it. This is one of the most intuitive ideas in all of physics, and light completely violates it. A photon can lose enormous amounts of energy, half its energy, 90% of its energy, and yet it never slows down. Not by a single meter per second. It keeps moving at exactly the same speed it must always travel. How is that possible? How can something lose energy without losing speed? The answer reveals something profound about the nature of light, energy, and the fabric of reality itself. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Something so basic, so deeply woven into your experience of the world that you have never once questioned it. When something loses energy, it slows down. Think about a ball. You throw it straight up into the air. The moment it leaves your hand, gravity starts pulling it back. The ball rises, but it rises more slowly with each passing instant. It is losing energy. Specifically, it is losing kinetic energy, the energy of motion, and that energy is being converted into gravitational potential energy as the ball climbs higher against gravity's pull. You can see this happening in real time because the ball is slowing down. It climbs higher, but the climb gets weaker and weaker. Eventually, at the very top of its arc, the ball stops completely. For one brief moment, it hangs motionless in the air. Its kinetic energy has dropped to zero. And then gravity takes over. The ball falls back, accelerating as it descends, regaining kinetic energy on the way down, speeding up until it returns to your hand at roughly the same speed it left with. The entire process is perfectly intuitive. Energy and speed rise and fall together. More energy means more speed. Less energy means less speed. Zero kinetic energy means zero speed. You have watched this happen 1,000 times. You have never once seen it work differently. This is not just a feeling or a casual observation. It is one of the most fundamental relationships in classical physics, understood mathematically for centuries. Isaac Newton laid the groundwork in the late 1600s when he formalized the laws of motion. The kinetic energy of any moving object depends on two things: its mass and its speed. More precisely, kinetic energy equals 1/2 times the mass times the velocity squared. This equation tells you something important. If you double an object's speed, the kinetic energy does not merely double, it quadruples. Triple the speed, and the kinetic energy increases 9 times. Speed has an outsized influence on energy, and the relationship runs both ways. If you remove energy from a moving object, its speed must drop. If you add energy, the speed must rise. Mass acts as the bridge that ties them together. As long as an object has mass, its energy and its speed are mathematically, physically, inseparably connected. You see this connection everywhere in daily life, and you rely on it constantly without even thinking about it. A car cruising down the highway carries kinetic energy. If you take your foot off the gas, friction and air resistance begin draining that energy away. The car slows down. Not because it decides to, but because energy is leaving its motion, converted into heat in the tires, warmth in the brake pads, turbulence in the air behind the vehicle. the less energy remains in the car's forward motion, the slower it goes. Eventually, if nothing replenishes the energy, the car stops. Energy gone, motion gone. A bullet fired from a rifle carries enormous kinetic energy, a small piece of metal, perhaps only 9 or 10 grams, moving at hundreds of meters per second. When that bullet strikes a thick target, it transfers its energy into the material. The target deforms, heat is generated, sound waves radiate outward from the impact, and the bullet slows down. If the target is thick enough, the bullet comes to a complete stop, embedded in the material. All of its kinetic energy has been converted into other forms, and its speed has dropped to 0. A spinning top on a table gradually loses rotational energy to friction where the tip contacts the surface. The spin slows. The top wobbles, then topples and lies still. A pendulum swings back and forth in a grandfather clock, each arc slightly shorter than the last, as air resistance and friction at the pivot steal tiny amounts of energy with every pass. A bowling ball on a lane gradually decelerates as friction drains kinetic energy away. A satellite in low Earth orbit slowly loses altitude because the thin upper atmosphere, even at hundreds of kilometers up, creates drag that removes orbital energy one collision at a time. Every single one of these examples tells exactly the same story. A story so consistent and so universal that it has become part of your basic wiring as a human being. Energy and motion are linked. Lose energy, lose speed. Gain energy, gain speed. This relationship holds for everything you have ever thrown, pushed, kicked, rolled, or watched move across a surface. From the smallest pebble skipping across a pond to the largest planet orbiting a star. If it has mass and it loses energy, it slows down. There are no exceptions in your everyday experience, not one. And that is exactly why light is so baffling. Because light is the exception. Light can lose energy. It can lose enormous amounts of energy. A photon, a single particle of light, can begin its journey carrying tremendous energy and arrive at its destination with only a small fraction of what it started with. A photon can lose half its energy, 90% of its energy, 99.9% of its energy. And yet it never slows down. Not by 1 meter per second, not by 1 millimeter per second. From the moment a photon is created to the moment it is absorbed, if it is traveling through empty space, through vacuum, it moves at exactly the same speed. The same speed it has always moved at. The same speed every photon in the history of the universe has moved at, regardless of how much or how little energy it carries. This seems flatly impossible. Everything you have ever observed tells you that losing energy means losing speed. But light does not follow that pattern. Light follows different rules entirely. And understanding why requires us to examine two properties that make photons fundamentally, qualitatively different from every massive object you have ever touched, held, thrown, or watched slow to a stop. The first property is mass, or more precisely, the complete absence of it. Every object you interact with in daily life has mass. Your body has mass. A rock has mass. The air in your lungs has mass. Even a speck of dust drifting in a beam of sunlight has mass. Mass is one of the most fundamental properties matter can possess. It gives objects weight in a gravitational field. It makes things resist being pushed, resist being accelerated, resist any change in their state of motion. The more massive something is, the harder it is to set in motion, and the harder it is to stop once moving. This resistance to changes in motion is called inertia, and inertia is directly proportional to mass. Mass is also the crucial ingredient in the kinetic energy equation. 1/2 times mass times velocity squared. Mass is sitting right there in the formula. It is the very reason that energy and speed are connected for ordinary objects. When a ball slows down and loses kinetic energy, the mass is what mediates that relationship. The mass remains constant, the speed changes, and the energy changes right along with the speed because the formula ties all three together. Mass is the anchor. Mass is the bridge. Mass is the thing that makes the entire energy-speed connection work. Photons do not have this anchor. Photons, the fundamental particles of light, have no rest mass. Not a tiny amount too small to detect, not an almost negligible mass rounded to zero for convenience, exactly zero. Precisely zero. This is not a measurement limitation or an approximation. It is a fundamental fact about the nature of photons, confirmed by every experiment ever conducted on the properties of light. Photons are massless particles. They carry energy. They carry momentum. They exert measurable pressure when they strike a surface, but they carry zero rest mass. And without mass, the kinetic energy formula does not merely give a different answer, it gives a meaningless one. If you plug zero mass into the equation 1/2 times mass times velocity squared, you get zero for every photon in existence. A faint radio wave photon drifting through the cosmos and a devastatingly powerful gamma-ray photon blasting out of a nuclear reaction would both have zero kinetic energy according to this formula. That is spectacularly, obviously wrong. Photons carry real, measurable energy. Sunlight warms the surface of the Earth. Concentrated laser beams slice through steel plates. Ultraviolet radiation causes painful sunburns on exposed skin. X-rays pass through flesh to reveal the bones beneath. Gamma rays destroy living tissue at the molecular level. Photon energy is real. It has real, tangible consequences. But it does not come from the relationship between mass and speed, because there is no mass to put into the equation. This is the first place where everyday intuition falls apart. The formula that connects energy and speed for everything you have ever experienced in your entire life does not apply to light. You need a completely different equation, a completely different framework to understand where photon energy comes from and why it can change without any change in speed. The second property that makes light fundamentally different is its speed. And this is where things become truly remarkable. When you drive a car, you can choose how fast to go. 10 kilometers per hour through a parking lot, 100 on the highway, 200 on a racetrack if you have the right vehicle and enough open road. Speed for a car is a variable. It changes depending on how much energy the engine provides and how much resistance the car faces from the road and the air. You can speed up, slow down, stop, go in reverse. The same is true for a ball, a bullet, a spacecraft, a planet. For any object with mass, speed is flexible. It is adjustable. It is one of the properties that changes when you add or remove energy. The speed of light in vacuum is not like this at all. The speed of light is not a variable, it is a constant. Approximately 299,792 kilometers per second. And this number does not change under any circumstances. It does not depend on how the light was created. It does not depend on how much energy the photon carries. It does not depend on whether the source of the light was moving toward you or away from you at the moment of emission. It does not depend on whether you, the observer, are moving or standing still. The speed of light in vacuum is always, under every conceivable circumstance, exactly the same value. This was one of the most shocking discoveries in the history of physics. For centuries, people assumed light speed would behave like every other speed. If you were riding on a moving train and you throw a ball forward, the ball's speed relative to someone standing beside the tracks is the train speed plus the ball's speed. Speeds add together. This seemed so obviously self-evidently true that no one questioned it seriously. But in 1887, two American physicists named Albert Michelson and Edward Morley performed an experiment that would crack this assumption open. Michelson and Morley reasoned that if light travelled through some kind of medium filling space, then Earth's motion through that medium should affect the measured speed of light. Earth orbits the Sun at about 30 kilometers per second. If you measured the speed of light in the direction Earth was moving, it should appear slightly different from the speed measured perpendicular to that direction. The difference would be small, but Michelson had designed an interferometer precise enough to detect it. They set up the experiment and measured with extraordinary care, and they found nothing. No difference at all. The speed of light was identical in every direction, regardless of how Earth was moving through space. The result stunned the physics community. It contradicted fundamental assumptions that had gone unchallenged for generations. Various explanations were proposed over the following years, but none were fully satisfying. The experimental result stood like a locked door that nobody had the key to. Then, in 1905, a 26-year-old clerk working in a Swiss patent office named Albert Einstein published a paper that opened that door and changed the course of human understanding forever. Einstein proposed something radical. He said the speed of light in vacuum is the same for all observers, regardless of how they are moving relative to each other or relative to the source of the light. This does not sound earth-shattering at first, but follow the logic carefully and watch where it leads. Imagine you are standing on the ground. A spacecraft flies past you at half the speed of light. Someone aboard turns on a flashlight pointing forward. Ordinary intuition says the light should be moving at 1.5 times the speed of light relative to you. The spacecraft's speed plus the light's speed. But Einstein said no. You measure the flashlight's beam moving at exactly the speed of light. Not 1.5 times, exactly 1 times. And the person on the spacecraft also measures their flashlight's beam at exactly the speed of light relative to themselves. Both observers, moving at vastly different velocities, get the same answer for the speed of the same beam of light. This seems logically impossible. If two people are moving at different speeds, how can they both measure the same velocity for the same beam of light? Something has to give. And Einstein showed what gives. Space and time themselves adjust. For the moving observer, time passes more slowly relative to the stationary observer. Distances along the direction of motion physically contract. These are not optical illusions. They are not tricks of measurement or artifacts of instruments. They are real physical changes to the flow of time and the geometry of space. The universe reshapes the very fabric of reality so that the speed of light comes out exactly the same for everyone, everywhere, always. The speed of light is not protected by accident. It is protected by the structure of space-time itself. This has been confirmed experimentally so many times and with such extraordinary precision that it stands among the most solidly established facts in all of science. Atomic clocks flown on high-speed aircraft return showing slightly less elapsed time than identical clocks that remained on the ground, exactly matching the predictions of special relativity down to the nanosecond. Particles in accelerators at facilities like the Large Hadron Collider are pushed to 99.99% of the speed of light, and these particles live dramatically longer than identical particles at rest, because, from our reference frame, time is passing far more slowly for them. Muons, subatomic particles created when cosmic rays slam into molecules in the upper atmosphere, have a half-life so short they should decay long before reaching the ground. Yet they arrive at the surface regularly and in large numbers because time dilation stretches their effective lifetimes from our perspective. Relativistic corrections are built into technologies you use every day. The timing systems inside particle accelerators, the calibration of instruments aboard interplanetary spacecraft, the synchronization of clocks on navigation satellites, all of these incorporate Einstein's equations as engineering necessities, not optional refinements. If special relativity were even slightly wrong, these technologies would fail. They do not fail. They work precisely, reliably, and repeatedly, confirming Einstein's predictions every second of every day. The constancy of light speed is not a hypothesis waiting for confirmation. It is not an untested conjecture. It is one of the most rigorously verified facts in the history of human knowledge. And this constant speed is not merely a maximum that light happens to reach. It is the only speed at which massless particles can travel in vacuum. A photon cannot travel at half the speed of light. It cannot coast along at 99% of the speed of light. It must travel at exactly the speed of light. This is a direct, unavoidable consequence of special relativity applied to particles with zero rest mass. Einstein's equations reveal precisely why massive objects cannot share this fate. As you try to accelerate a massive object closer and closer to the speed of light, something dramatic happens. The energy required does not increase gradually or proportionally. It increases without limit. The closer you get, the more energy each additional tiny increment of speed demands. To reach 90% of light speed requires substantial energy. To reach 99% requires enormously more. To reach 99.9% requires more energy still by a staggering factor. And to actually reach 100%, to push a massive object to the full speed of light, would require truly infinite energy. Since infinite energy does not exist anywhere in the universe, no object with mass can ever reach light speed. This is not an engineering problem. It is not a technological limitation we might solve with better rockets or more powerful engines. It is a fundamental, permanent barrier built into the architecture of spacetime. But massless particles face no such barrier. They do not need to be accelerated to light speed from some slower starting velocity. They are created already moving at light speed. From the very first instant of a photon's existence, it is traveling at the speed of light. It has never moved at any other speed. It never will move at any other speed. This is not a choice, it is a requirement. The geometry of spacetime simply does not permit any other velocity for a particle carrying zero rest mass. This means the speed of a photon in vacuum is permanently, irrevocably locked. There is no physical process anywhere in the universe that can make a photon in vacuum move faster or slower. You cannot slow down a photon by removing energy from it. You cannot speed up a photon by adding energy to it. The speed is fixed. It is a structural constant of reality itself, and it applies identically to every photon that has ever existed or will ever exist, regardless of how much or how little energy that photon carries. Now hold both of these facts in your mind at the same time. Fact 1. Photons have no rest mass. The classical kinetic energy formula does not apply to them. Their energy is not determined by the relationship between mass and speed. Fact 2. Photons in vacuum travel at a fixed, invariant speed that cannot increase or decrease under any circumstances. These two facts together create the paradox. If a photon's energy is not stored in its speed, and its speed cannot change, then what exactly is photon energy? What property of the photon carries it? And when a photon loses energy, what physically changes about it if it is not the speed? To fully appreciate how strange this situation is, think of it as two completely separate stories about how energy works in the universe. Story 1 is the story of massive objects. A ball, a car, a planet. For these things, kinetic energy is directly, mathematically linked to speed through the formula involving mass. When energy is added, speed increases. When energy is removed, speed decreases. At zero kinetic energy, the object sits still. Speed is the container that holds the energy. You can always tell how much kinetic energy a massive object has by measuring how fast it moves. This story is intuitive. It is familiar. It governs everything from falling raindrops to orbiting spacecraft. Every human being on Earth understands this story instinctively because we have lived it every single day of our lives. Story 2 is the story of massless particles, photons. For these entities, speed is not a variable at all, it is a constant. Energy is not connected to speed in any way. The photon's energy depends on a completely different property, a property that can change freely, increasing or decreasing without limit, without ever affecting how fast the photon moves through space. When a photon loses energy, it does not slow down. Something else changes instead, and when a photon gains energy, it does not speed up. That same property shifts in the other direction. Speed stays locked, energy changes. And the thing that changes is something entirely separate from velocity. The mistake nearly everyone makes when first encountering this topic is applying story 1 to photons. People hear that light loses energy, and they automatically, instinctively assume it must be slowing down. That is the only possibility their experience has ever presented to them. But photons are not balls, they are not bullets, they are not cars coasting to a halt. They do not obey the same equations. They live in a fundamentally different category of physical existence, governed by fundamentally different rules. And the rules that govern massless particles are genuinely, deeply different from the rules that govern massive ones. The connection between energy and speed that works so perfectly for a baseball exists only because the baseball has mass. Remove the mass, and that connection vanishes entirely. What replaces it is something more subtle, more elegant, and ultimately more revealing about the true nature of energy. Before we explore what that replacement is, let's clear away some misconceptions that are so persistent and so widely believed that they will keep causing confusion unless we address them directly. The first misconception is that lower energy photons move more slowly. Many people assume that a feeble, low-energy radio wave must be crawling through space compared to an intense, high-energy gamma ray. This is completely wrong. In vacuum, a radio wave photon and a gamma ray photon travel at precisely the same speed. 299,792 kilometers per second. Not roughly the same speed, not approximately, identically. If you released a radio wave and a gamma ray side by side into empty space, aimed at the same distant target, they would arrive at exactly the same instant. You could not use speed to distinguish them. A photon carrying 1 billion times more energy than another photon crosses any distance in exactly the same amount of time. Energy and speed are completely decoupled for light in vacuum. The second misconception is that light gets tired. Some people picture photons gradually wearing themselves out as they travel through space, as if the journey itself is exhausting, as if moving through the vacuum costs them something. This image is completely false. A photon does not expend energy to travel. For a massless particle moving through vacuum, travel requires no effort whatsoever. There is no friction in empty space. There is no drag. There is no resistance of any kind. A photon could cross the entire observable universe, traveling for over 13 billion years, and the mere act of traveling would not drain a single unit of energy from it. When photons do lose energy, and they genuinely do in certain circumstances, it is because of specific physical processes acting upon them from outside. The photon does not tire. The photon does not fatigue. Something in the environment shifts its properties. The third misconception is that light uses energy as fuel to maintain its speed, the way a car burns gasoline to overcome friction. In this picture, the photon is constantly spending energy to keep itself in motion, and when its energy reserves run low, it slows down and eventually stops. This is wrong at every level. A photon does not need fuel. It does not overcome resistance. Nothing in vacuum is trying to slow it down. And even if something were, deceleration is not something a photon is capable of doing. Slowing down is not physically possible for a massless particle in vacuum. Speed is not maintained by burning through an energy supply. Speed is a fixed, permanent consequence of having zero rest mass in the framework of spacetime. The photon moves at the speed of light because the geometry of reality demands it, not because the photon is working to maintain that speed, not because it is spending precious reserves, because the structure of the universe permits no other option for something without mass. All three of these misconceptions arise from the same root cause. People take the rules that apply to massive objects, objects with mass that slow down as they lose energy, and they project those rules onto light. This projection seems natural, it seems logical, but it is wrong. Photons are not massive objects. They do not have mass. They do not obey the same equations. And the intuitions that serve you brilliantly well for baseballs and automobiles will lead you astray every single time you try to apply them to particles of light. So, if speed is permanently locked and mass is zero, what actually carries a photon's energy? When light loses energy without slowing down, what is the thing that changes? The answer has been hiding in plain sight. You have experienced it every single day of your life without realizing its deep significance. Every time you have seen a rainbow arching across the sky after a rainstorm and noticed the colors spreading from red on the outside to violet on the inside. Every time you have felt the difference between the warm red glow of a sunset and the harsh, bright blue of a clear midday sky. Every time you have seen the green of a traffic light or the orange flicker of a candle flame, you have been looking directly at the answer. The answer is frequency. A photon's energy is determined not by how fast it moves through space, but by how rapidly its electromagnetic field oscillates. Light is an electromagnetic wave. It is a self-sustaining ripple in electric and magnetic fields that propagates through space at that fixed, invariant speed. And like all waves, it has a frequency, the number of complete oscillations per second, and a wavelength, the distance between successive wave crests. These two properties are related to each other through the speed of light. Higher frequency means shorter wavelength. Lower frequency means longer wavelength. And every single one of these waves, regardless of its frequency, travels at exactly the same speed in vacuum. A low-frequency radio wave and a high-frequency gamma ray cross empty space at precisely the same velocity. The connection between frequency and energy turns out to be one of the deepest relationships in all of physics. It was not discovered easily. It took a revolution in thinking at the turn of the 20th century, a revolution so radical that even the physicist who started it could not bring himself to fully accept what he had found. What emerged from that upheaval was an insight that completely redefined how energy works for light. The energy carried by a photon is not stored in its motion through space. It is stored in the character of its oscillation. How rapidly the electromagnetic field vibrates determines how much energy the photon carries. Nothing else. Not speed, not brightness, not intensity, frequency alone. This discovery introduced a single equation that changed the course of physics forever. An equation that tells you precisely how much energy a photon carries based solely on its frequency. An equation that makes the paradox of light losing energy without slowing down not only understandable, but inevitable. Because once you know that energy is tied to frequency, you understand immediately what happens when a photon loses energy. The frequency decreases. The wavelength stretches. The photon shifts toward the red end of the spectrum. But the speed remains exactly the same. Because speed and frequency are independent properties of a photon. Changing one does not change the other. This is the key insight. This is the piece that makes the entire puzzle click into place. A photon's speed is fixed by the structure of spacetime and the laws of electromagnetism. A photon's energy is carried by its frequency, and frequency can change. It can increase when a photon gains energy. It can decrease when a photon loses energy, all without altering the photon's speed by even the smallest imaginable fraction. The ball that you threw into the air slows down when it loses energy, because for a ball, energy lives in speed. The photon that crosses the universe does not slow down when it loses energy, because for a photon, energy lives in frequency. Different container, different rules, same universe. What makes a photon shift its frequency? What physical processes can change the energy of light while leaving its speed completely untouched? It turns out there are several, and they are among the most beautiful and profound phenomena in all of physics. Gravity can do it. The expansion of space itself can do it. Even the simple relative motion between a light source and an observer can do it. Each of these processes changes the measured frequency of a photon, shifting its energy up or down, while the photon continues to travel at exactly the speed it must always travel. That is what we are going to explore next. At the end of the 1800s, physics was in crisis. Not a quiet philosophical crisis debated over dinner parties, a genuine mathematical, the equations are giving impossible answers crisis. And the problem centered on something deceptively simple: heat. When you heat a piece of metal, it glows. You have seen this yourself. A blacksmith heats iron in a forge. At first, the metal does not visibly glow, though it radiates heat you can feel on your skin from several feet away. That invisible radiation is infrared light, electromagnetic waves with frequencies too low for your eyes to detect, but perfectly capable of warming your hands. As the temperature rises further, the metal begins to glow a deep, dull red. Hotter still, it shifts to bright orange, then yellow, then eventually a blinding white if the temperature gets high enough. The color changes because the dominant frequency of the emitted light increases as the temperature rises. Cooler objects radiate lower frequency light. Hotter objects radiate higher frequency light. This relationship between temperature and emitted radiation had been studied for decades. Physicists had very precise measurements of exactly how much energy a hot object radiates at each frequency. The data was solid. The curves were well mapped. All they needed was a theory that explained those curves. And this is where everything fell apart. Using the best physics available at the time, classical thermodynamics and electromagnetism, physicists tried to derive a formula that matched the observed radiation curves. They could get the low-frequency end of the curve to work, or they could get the high-frequency end to work, but no single formula could describe both. Worse, when they tried to calculate the total energy radiated across all frequencies, the classical equations predicted something absurd. At high frequencies, the energy should increase without limit. The equations said that any warm object, a candle, a brick, even a human body, should be emitting infinite energy in the ultraviolet range and beyond. This obviously did not happen. If it did, sitting next to a campfire would kill you instantly with a burst of lethal radiation. The mathematical prediction of infinite energy at high frequencies became known as the ultraviolet catastrophe, and it was a genuine catastrophe for physics because it meant something fundamental about the existing framework was wrong. In the year 1900, a German physicist named Max Planck found a way out, and his solution was so strange, so unlike anything physics had ever proposed before, that even Planck himself was uncomfortable with it. Planck discovered that if he assumed energy was not continuous, but came in tiny, discrete packets, the mathematics worked perfectly. The radiation curves matched the experimental data at every frequency, at every temperature, with no infinities, no absurdities. The fix was elegant, but it required accepting something radical. Energy, which everyone had always assumed flowed smoothly, like water from a tap, actually came in individual droplets. Planck called these droplets quanta, from the Latin word for how much. And the size of each quantum was not random. It was determined by one thing: the frequency of the radiation. The relationship Planck discovered was breathtakingly simple. The energy of a single quantum equals a constant times the frequency. That constant, the proportionality factor linking energy to frequency, is now called Planck's constant. It is an extraordinarily tiny number, approximately 6.626 times 10 to the negative 34 joule seconds. This number is so small that at the scales of everyday life, the individual quanta are far too tiny to notice. Energy appears to flow continuously because the droplets are so minuscule that trillions upon trillions of them arrive every instant, blending together into what seems like a smooth stream. But at the atomic scale, the droplets matter. They change everything. Planck initially thought his quantization was just a mathematical convenience, a clever device that happened to give the right answer. He expected someone to eventually find a deeper explanation that restored continuity. That did not happen. Instead, 5 years later, Albert Einstein took Planck's idea and pushed it further than Planck himself was willing to go. In 1905, the same extraordinary year in which Einstein published his paper on special relativity, he also published a paper on the photoelectric effect that would eventually earn him the Nobel Prize. The photoelectric effect was a puzzling phenomenon. When light shines on certain metals, it can knock electrons free from the surface. Classical physics predicted that the energy of the ejected electrons should depend on the brightness of the light. Brighter light means more energy hitting the surface, which should mean more energetic electrons. But experiments showed something completely different. The energy of the ejected electrons depended not on brightness, but on the color of the light, its frequency.
Blue light with higher frequency ejected electrons with more energy. Red light with lower frequency ejected electrons with less energy. And below a certain threshold frequency, no electrons were ejected at all, no matter how blindingly bright the light was. You could flood the surface with the most intense red light imaginable, and not a single electron would budge. But even a faint beam of blue light above the threshold frequency would knock electrons free immediately. Classical wave theory could not explain this, but Einstein could. He proposed that light itself is quantized, not just the emission process, as Planck had cautiously suggested, but the light itself. Light consists of individual particles, quanta of electromagnetic energy, each carrying a specific amount of energy determined by its frequency. Einstein called these particles light quanta. We call them photons today. Each photon carries energy equal to Planck's constant times the frequency of the light. This is the equation: E equals h times f. E is the energy, h is Planck's constant, f is the frequency. That is it. That single compact equation tells you everything about how much energy a photon carries. And the only variable on the right side of the equation, the only thing that can change, is the frequency. Planck's constant is a fixed number. It never changes. So the energy of a photon is locked to its frequency. High frequency means high energy. Low frequency means low energy. And nothing else matters. Not the brightness, not the intensity, not the speed. A single photon of blue light carries more energy than a single photon of red light because blue light has a higher frequency. Period. The speed of both photons is identical. The mass of both photons is 0. The only thing that distinguishes them energetically is how rapidly their electromagnetic fields oscillate. This was the revolution. This was the moment when physics broke free from the old framework that demanded energy and speed be connected through mass. For photons, mass is absent and speed is fixed. Frequency is the variable that carries the energy. And once you understand this, the paradox of light losing energy without slowing down dissolves completely. Because losing energy for a photon does not mean slowing down. It means oscillating less rapidly. It means the frequency drops. The wavelength stretches. The photon shifts toward the red end of the spectrum, but its speed through vacuum remains exactly what it has always been. 299,792 kilometers per second. Unchanged, untouched, invariant. To truly appreciate what this means, consider the electromagnetic spectrum. Because what we call visible light is only a tiny sliver of a much broader landscape of electromagnetic radiation. And every part of that landscape travels at the same speed, separated only by frequency. At the lowest frequencies, far below anything your eyes can detect, are radio waves. These are the photons that carry music to your car stereo, television signals to your screen, and wireless data to your phone. Radio wave photons have frequencies ranging from a few thousand hertz to a few hundred gigahertz. Their wavelengths can be enormous, from kilometers long down to millimeters. And their individual photon energies are fantastically low. A single radio photon carries so little energy that it would take an unimaginable number of them arriving together to produce any noticeable effect. This is why radio communication works. The transmitter sends trillions upon trillions of photons per second, and together they carry enough combined energy to induce a measurable electrical current in your antenna. But each individual photon is almost inconceivably weak. Above radio waves come microwaves. These have higher frequencies, shorter wavelengths, and more energy per photon than radio waves. Your microwave oven uses photons with a frequency of about 2.45 gigahertz. At this frequency, the photons interact strongly with water molecules, causing them to vibrate and generate heat. This is why microwaves heat your food. The photons are tuned to a frequency that water molecules absorb efficiently. Next comes infrared radiation. You cannot see infrared, but you can feel it. The warmth from a campfire, from a space heater, from sunlight on your skin, that is infrared. These photons have higher frequencies and more energy per photon than microwaves. Your body radiates infrared constantly, which is how thermal imaging cameras detect people in darkness. They are detecting the infrared photons your warm body emits. Then comes visible light. This is the narrow band of frequencies your eyes evolved to detect, roughly from 400 trillion hertz to 750 trillion hertz. Within this band, different frequencies produce different color perceptions. The lowest visible frequencies appear red. As frequency increases, you perceive orange, then yellow, then green, then blue, then violet at the highest visible frequencies. Red photons carry less energy than violet photons, but they do not travel slower. A red photon and a violet photon released at the same moment from the same location will arrive at any destination at exactly the same time. They are both traveling at the speed of light. Their energies are different because their frequencies are different, not because one is lagging behind the other. Think about this carefully, because it directly contradicts what many people assume. A deep red photon from a dying ember and an intense violet photon from a powerful laser cross a vacuum at precisely the same speed. If you lined them up at a starting line and set them loose toward a finish line 1 billion kilometers away, they would cross that line in a dead tie. You could not tell which was the high-energy photon and which was the low-energy photon by watching their speed. The only way to tell them apart is to measure their frequency. Speed tells you nothing about a photon's energy. Frequency tells you everything. Above visible light comes ultraviolet radiation. Your eyes cannot see it, but your skin certainly reacts to it. Ultraviolet photons carry enough energy per photon to damage the molecular bonds in your DNA, which is why prolonged sun exposure causes sunburn and increases the risk of skin cancer.
The individual photons in ultraviolet light are more energetic than visible light photons one by one. This is why ultraviolet is more dangerous. It is not because the light is moving faster. It is because each photon packs a harder punch. Each oscillation is more rapid. Each quantum of energy is larger. Higher still are X-rays. These photons have frequencies hundreds to thousands of times higher than visible light. Their individual photon energies are high enough to pass through soft tissue but be absorbed by dense bone. This is why X-ray images reveal your skeleton. The photons carry enough energy per photon to penetrate flesh but get stopped by the calcium and phosphorus in your bones. Wilhelm Röntgen discovered X-rays in 1895 and was so uncertain about what they were that he named them X-rays, with X standing for unknown. At the very top of the energy scale are gamma rays. These are the highest frequency, shortest wavelength, most energetic photons in the universe. Gamma rays are produced in nuclear reactions, in the cores of exploding stars, in the violent regions near black holes. A single gamma ray photon can carry millions or even billions of times more energy than a single photon of visible light. These photons are so energetic that they can shatter atomic nuclei, create particle-antiparticle pairs out of empty space, and destroy biological tissue at the molecular level. Gamma-ray bursts, the most energetic explosions in the universe, release more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. And here is the critical point. Every single one of these photons, from the feeblest radio wave to the most devastating gamma ray, travels through vacuum at exactly the same speed. 299,792 kilometers per second. No exceptions. The gamma ray photon, carrying billions of times more energy than the radio wave photon, does not travel billions of times faster. It does not travel even slightly faster. The two photons are indistinguishable by speed. They are separated only by frequency. Only by how rapidly their fields oscillate. Only by the energy each individual quantum carries. This is what makes the electromagnetic spectrum so remarkable. It is a single phenomenon, electromagnetic radiation, obeying a single set of laws, traveling at a single speed, but manifesting in astonishingly diverse ways depending on frequency alone. Radio waves warming the coil of your antenna, microwaves heating your leftovers, infrared warming your face by the fireplace, visible light illuminating the page you read, ultraviolet triggering chemical reactions in your skin, X-rays revealing the fracture in your wrist, gamma rays sterilizing medical equipment in sealed chambers. All the same thing, all photons, all traveling at the same speed, differing only in frequency. Now let's return to the central question. What does it actually mean, physically, for a photon to lose energy? For a massive object, losing energy means slowing down. The ball decelerates. The car coasts to a halt. The bullet embeds in its target. Speed drops, motion weakens. This process is visible, intuitive, and directly connected to the energy loss through the kinetic energy equation. For a photon, losing energy means something entirely different. The photon's frequency decreases. Its electromagnetic field oscillates less rapidly. And because frequency and wavelength are inversely related at the fixed speed of light, the wavelength gets longer. The photon stretches. If the photon began as visible light, it shifts toward the red end of the spectrum. If it was already red, it shifts further into infrared. If it was infrared, it can shift into microwave or even radio frequencies. Each step down in frequency is a step down in energy. The photon carries less energy per quantum. It becomes a weaker, gentler, more languid oscillation. But it never, at any point, slows down. The speed remains locked at the speed of light in vacuum. The photon just vibrates less energetically while maintaining the same relentless forward pace through space. This process, this measurable decrease in photon frequency, has a name. It is called redshift. The term comes from the fact that visible light losing energy shifts toward the red end of the visible spectrum, because red is the lowest frequency color your eyes can see. But redshift applies far beyond the visible range. A gamma-ray photon losing energy shifts toward the X-ray range. An X-ray photon losing energy shifts toward ultraviolet. A microwave photon losing energy shifts toward radio waves. In every case, the mechanism is the same. The frequency drops. The wavelength lengthens. The energy decreases. And in every case, the speed in vacuum remains exactly the same. Redshift is not a theoretical abstraction. It is measured constantly by astronomers, physicists, and engineers around the world. Every time you see a headline about a distant galaxy being billions of light years away, that distance was almost certainly determined by measuring the redshift of the galaxy's light. Astronomers observe the light arriving from the galaxy, measure the frequencies of specific spectral lines, and compare those frequencies to the known frequencies of the same spectral lines measured in a laboratory here on Earth. If the observed frequencies are lower than the laboratory values, the light has been redshifted. It has lost energy. And the amount of redshift tells you something precise about the physical process that caused it.
And there is a corresponding opposite effect. If a photon gains energy instead of losing it, the frequency increases, the wavelength shortens. The photon shifts toward the blue end of the spectrum. This is called blue shift. A blue shifted photon has gained energy. Its electromagnetic oscillation is more rapid. It carries more energy per quantum. But again, the speed is unchanged. Whether shifting red or shifting blue, whether losing energy or gaining it, the photon's velocity through vacuum is permanent and fixed. Only the frequency moves. Only the energy changes. The beauty of this arrangement lies in how cleanly it resolves the paradox we began with. The paradox only existed because we were using the wrong mental model. We were trying to understand photon energy by analogy with massive objects, where energy and speed are bound together by mass. But photons have no mass. The binding does not exist. For photons, energy and speed are two completely independent properties. Speed is set by the structure of spacetime. Energy is set by frequency. You can change one without touching the other. The universe is not being contradictory or paradoxical. It is being perfectly consistent. We were just applying the wrong rules. This also tells us something profound about what energy actually is for a massless particle. For a massive object, energy is stored in motion. A faster object has more energy. A slower object has less. But for a photon, energy is stored in the character of the oscillation. A more rapidly oscillating photon has more energy. A more slowly oscillating photon has less. The photon is not moving through space more or less energetically. It is vibrating more or less energetically while moving through space at a constant rate. Think of it this way. Imagine two people walking side by side at exactly the same pace, covering exactly the same distance in exactly the same time. One person is calmly strolling with their arms relaxed at their sides. The other person is vigorously waving their arms up and down as they walk. Both people are moving forward at the same speed, but one is doing something extra, something energetic, something that requires more energy to sustain. The arm waving does not make the person walk faster. It is an additional form of activity layered on top of the forward motion. Now imagine you could gradually slow down the arm waving. The person keeps walking at the same pace, but waves their arms less and less vigorously. Eventually, they stop waving entirely and just walk calmly. Their forward speed has not changed at all, but the energy associated with the arm waving has decreased to zero. This analogy is imperfect, as all analogies for quantum phenomena must be. Photons are not people waving their arms, but the analogy captures the essential idea. The forward motion through space is fixed and constant for all photons. The oscillation of the electromagnetic field is the variable part. the part that carries the energy, the part that can increase or decrease without affecting the forward speed. And now we arrive at the question that opens the next stage of this journey. If frequency is what carries a photon's energy, and if frequency can change while speed stays fixed, then what physical processes in the universe are capable of changing a photon's frequency? What can reach out and shift the oscillation of a photon, stealing energy from it or adding energy to it, without ever altering how fast it moves? It turns out the universe has several such mechanisms, and they are among the most profound and beautiful phenomena ever discovered. The simplest and most familiar is the Doppler effect. You have experienced the Doppler effect with sound waves countless times, whether or not you knew the name. When an ambulance approaches you with its siren blaring, the pitch of the siren sounds higher than it really is. As the ambulance passes and drives away from you, the pitch drops noticeably lower. The siren itself is not changing. The ambulance driver hears the same steady pitch the entire time. What changes is the relative motion between you and the source. As the ambulance approaches, the sound waves get compressed in front of it. More wave crests arrive at your ear per second, meaning a higher frequency, meaning a higher pitch. As it recedes, the waves get stretched behind it. Fewer crests arrive per second, meaning a lower frequency, meaning a lower pitch. Light does the same thing. When a source of light moves toward you, the light it emits gets compressed. The frequency increases. The photons are blue shifted. They carry more energy. When a source of light moves away from you, the light gets stretched. The frequency decreases. The photons are red shifted. They carry less energy. And in both cases, the photons are still traveling at exactly the speed of light. It is only the frequency that has changed. The relative motion between the source and the observer shifts the measured frequency without altering the speed of propagation. This is how astronomers first discovered that most galaxies in the universe are moving away from us. In the 1920s, Edwin Hubble measured the light from dozens of distant galaxies and found that their spectral lines were systematically shifted to lower frequencies, redshifted. The farther away a galaxy was, the greater the redshift. The galaxies were receding, and the light they emitted was losing energy as a result. Not because the photons were slowing down, because the measured frequency was decreasing due to the relative motion between the galaxy and Earth. But the Doppler effect, while important, is only the beginning. There are redshift mechanisms far stranger and far more profound than simple relative motion. Mechanisms that do not involve any movement of the source or the observer at all. Mechanisms rooted in the deepest properties of spacetime itself. One of these mechanisms involves gravity. Not gravity pulling on a photon the way it pulls on a ball. That picture does not work for light, as we have already established. Instead, gravity affects light through something far more subtle, something that required Einstein to completely reimagine what gravity actually is before anyone could even conceive of it. He published that reimagining in 1915, and it predicted something astonishing about the relationship between gravity and the frequency of light. Something that took decades to confirm experimentally. Something that is now so precisely understood that it is built into technology you carry in your pocket and use every single day without thinking about it. And near the most extreme objects in the universe, this effect becomes so powerful that it can strip virtually all the energy from a photon, while the photon continues to travel at exactly the speed of light. Gravity does not slow the photon down. It does something far more strange. Understanding what requires us to rethink everything we believe about the nature of space, time, and the relationship between them. The other mechanism operates on an even grander scale. It involves a property of the universe itself that was not even suspected until the 20th century. A property so surprising that Einstein refused to believe his own equations when they first predicted it. A property so vast in its consequences that it has been quietly, relentlessly reshaping the energy of every photon crossing the cosmos for billions of years. This mechanism has no parallel in everyday experience. It does not involve any object exerting any force on any photon. It does not involve motion through space in any ordinary sense. And yet it has drained more energy from more photons over a longer span of time than any other process in the history of the universe. The most ancient light in existence has been transformed by this mechanism so thoroughly that it is now barely detectable. A faint whisper where there was once a blinding shout. And through all of that transformation, not a single photon slowed down by even a fraction of a meter per second. These two mechanisms, one rooted in the nature of gravity and one rooted in the behavior of the cosmos on its largest scales, represent the deepest ways the universe can reshape a photon's frequency without touching its speed. Neither operates through collisions, neither involves friction or drag, neither requires the photon to spend a single quantum of energy on the process. They are consequences of the structure of spacetime itself, woven into the architecture of reality at its most fundamental level. Gravity's effect on light is where we turn next, and it reveals something extraordinary about the relationship between energy, frequency, and the fabric of space and time itself. Gravity, in the way most people think about it, is a force that pulls things down. You drop a ball, and gravity pulls it toward the floor. You jump, and gravity pulls you back to the ground. The moon stays in orbit because gravity pulls it toward Earth. Earth stays in orbit because gravity pulls it toward the sun. This picture of gravity as a pulling force was the foundation of physics for over 2 centuries, from the moment Isaac Newton published his law of universal gravitation in 1687 until the early 20th century. And for nearly everything you encounter in daily life, it works beautifully. It predicts the arc of a thrown baseball. It calculates the orbits of satellites. It explains why the ocean has tides. Newton's gravity is one of the most successful theories in the history of science. But Newton's gravity has a problem. It cannot explain what gravity actually is. It tells you how gravity behaves. It gives you equations that predict gravitational effects with impressive accuracy. But it treats gravity as a mysterious force that acts instantaneously across empty space, reaching out from one mass to another with no explanation of how. Newton himself was deeply troubled by this. He wrote that the idea of one body acting on another through a vacuum without any intermediary was so absurd that no person with a competent faculty of thinking could ever accept it. He gave us the math, but the mechanism remained a mystery. In 1915, Albert Einstein provided the mechanism, and it was nothing like what anyone expected. Einstein's general theory of relativity reimagined gravity completely. In Einstein's framework, gravity is not a force pulling objects through space. Gravity is the curvature of spacetime itself. Massive objects do not reach out and tug on nearby things. Instead, they warp the fabric of space and time around them, and objects moving through that warped fabric follow curved paths. The Earth does not pull the moon toward it with an invisible rope. The Earth bends the space-time around it, and the moon follows the straightest possible path through that curved geometry. That path happens to be a closed orbit. From the moon's perspective, it is not being pulled. It is simply moving forward through space. But space itself is curved, so forward means around. This was a profound conceptual revolution. Space and time are not a passive, rigid stage on which events unfold. They are dynamic, flexible, responsive to the presence of mass and energy. Where mass is concentrated, space-time curves. Where space-time curves, objects follow curved paths. This is gravity. Not a force, but geometry. And this geometric picture of gravity has a direct, measurable, experimentally confirmed consequence for light. If space-time is curved near massive objects, then light travelling through that curved space-time must be affected by the curvature. Photons follow the geometry of space-time
just as everything else does. And when a photon travels through a region where space-time is curved by a massive object, something remarkable happens to its frequency. Imagine a photon emitted from the surface of a massive star.
The photon is created with a certain frequency, a certain energy, determined by the physical process that produced it. Perhaps an atom on the star's surface undergoes a transition between energy levels, emitting a photon with a precise, well-defined frequency. This frequency is a fingerprint. Every element produces photons at specific characteristic frequencies when its atoms transition between energy levels. Hydrogen has its set of frequencies. Helium has a different set. Iron has yet another. These spectral fingerprints are so reliable that astronomers use them constantly to identify the chemical composition of distant objects. Now the photon begins its journey outward, away from the star's surface, climbing through the star's gravitational field. In Newton's picture, you might imagine the photon being pulled back by gravity, slowing down, losing speed the way a ball thrown upward slows down. But we already know this cannot happen. The photon cannot slow down. It must travel at the speed of light, always, without exception. What happens instead is far more subtle and far more interesting. The photon's speed remains exactly constant, but its frequency changes. An observer far away from the star, out in the relative flatness of empty space, measures the arriving photon and finds that its frequency is lower than it was at the moment of emission. The photon has been redshifted. It has lost energy, but it has not lost speed. The energy loss is encoded entirely in the decrease of frequency. This is gravitational redshift, and it arises directly from the curvature of space-time near the massive object. The connection between gravitational redshift and the curvature of space-time runs through one of the most elegant ideas in all of physics, the equivalence principle. Einstein arrived at this principle through a thought experiment he later called the happiest thought of his life. He imagined a person standing in an elevator on the ground floor of a building. The person feels their own weight. Their feet press against the floor. If they drop a ball, it falls. Now imagine the same elevator in deep space, far from any massive object, being accelerated upward by a rocket at exactly the same rate as gravitational acceleration on Earth's surface. The person inside would feel exactly the same weight. If they dropped a ball, it would fall at exactly the same rate. Every experiment they could perform inside the elevator would give exactly the same result in both situations. There is no measurement, no observation, no test that would tell them whether they are in a gravitational field or being accelerated through empty space. Einstein realized this was not a coincidence. It was a fundamental principle. Gravity and acceleration are equivalent. Locally, in a small enough region, you cannot distinguish between the two. This equivalence principle became the foundation of general relativity, and it has a direct implication for light. Imagine you are in an accelerating elevator in deep space. A photon enters through a small hole in the wall near the floor. Because the elevator is accelerating upward while the photon crosses the interior, the photon's path appears to curve downward relative to the elevator. It enters near the floor on one side and hits lower on the opposite wall. From inside the elevator, it looks like the photon is falling, curving downward just as a ball would. Since the equivalence principle says gravity and acceleration are indistinguishable, the same must happen in a gravitational field. Light must bend in the presence of gravity. This was one of Einstein's earliest predictions, and it was spectacularly confirmed in 1919, when Arthur Eddington observed starlight bending around the sun during a solar eclipse. But the equivalence principle tells us more than just that light bends. It tells us that light changes frequency in a gravitational field. Here is why. Imagine a photon emitted from the floor of the accelerating elevator, directed upward toward a detector on the ceiling. While the photon is in flight, the elevator continues to accelerate. By the time the photon reaches the ceiling detector is moving slightly faster than the floor emitter was when the photon left. This relative velocity between emitter and detector produces a Doppler shift. the detector measures a slightly lower frequency than the emitter produced. The photon has been redshifted, not because anything happened to the photon itself, but because the detector is moving relative to the emitter due to the ongoing acceleration. The equivalence principle demands that the same thing must happen in a gravitational field. A photon emitted near a massive object and received at a higher point in the gravitational field must arrive with a lower frequency. The photon climbing out of the gravitational well is redshifted. It loses energy, its frequency decreases, and its speed remains exactly constant at the speed of light. This prediction was extraordinarily precise and quantitative. Einstein's equations told you exactly how much the frequency would shift for a given gravitational field strength and a given height difference. It was not a vague, qualitative prediction. It was a specific, testable number. But testing it was extremely difficult. The effect is tiny in ordinary gravitational fields. On Earth's surface, the gravitational redshift between the floor and the ceiling of a room is so minuscule that no instrument available in Einstein's time could detect it. The frequency shift over a height difference of a few meters is only about 1 part in 10,000 trillion. You would need a way to measure frequency with almost unbelievable precision. It took over 4 decades before technology caught up with the theory. In 1959, 2 physicists at Harvard University, named Robert Pound and Glenn Rebka, performed an experiment that is now considered one of the most elegant confirmations of general relativity ever conducted. Pound and Rebka used the Jefferson Tower at Harvard, a building roughly 22.5 meters tall. They placed a source of gamma rays at the top of the tower and a detector at the bottom, then reversed the arrangement with the source at the bottom and the detector at the top. The gamma rays were emitted by iron 57 nuclei through a process that produces photons at an exceptionally precise frequency. The key to the experiment was a recently discovered phenomenon called the Mossbauer effect, which allowed the emission and absorption of gamma rays with almost no energy lost to recoil of the emitting or absorbing nucleus. This meant the gamma rays had an extraordinarily narrow frequency range, narrow enough that even the minuscule gravitational redshift over 22.5 meters would be detectable. When gamma rays traveled upward from bottom to top, climbing against Earth's gravitational field, their frequency was slightly lower when they arrived at the detector. They had been gravitationally redshifted. When the setup was reversed and gamma rays traveled downward from top to bottom, falling into the gravitational field, their frequency was slightly higher on arrival. They had been gravitationally blue-shifted. The measured shifts matched Einstein's prediction to within 10%, a remarkable achievement given the extraordinary subtlety of the effect. Later refinements of the experiment brought agreement to within 1%. This was direct, laboratory-scale confirmation that gravity changes the frequency of light. Photons climbing out of a gravitational field lose energy. Photons falling into a gravitational field gain energy. And in both cases, the speed of the photons remained exactly the speed of light. Only the frequency changed. You might wonder what this has to do with your everyday life. The answer is more than you might think. If you have ever used a GPS device to navigate, you have relied on the reality of gravitational redshift without knowing it. GPS works by comparing signals from multiple satellites orbiting Earth. Each satellite carries an extremely precise atomic clock and broadcasts the time according to that clock. Your GPS receiver picks up signals from several satellites, compares the arrival times, and uses the differences to calculate your position. The entire system depends on the satellite clocks being extraordinarily accurate. Even tiny timing errors translate into significant position errors. A clock error of just 1/1,000,000th of a second corresponds to a position error of about 300 meters. Here is the problem. The GPS satellites orbit at an altitude of about 20,200 kilometers above Earth's surface. At that altitude, they are much farther from Earth's center than you are on the ground.
General relativity predicts that clocks farther from a massive object tick faster than clocks closer to it, because the curvature of spacetime is weaker at greater distances. This is the same phenomenon as gravitational redshift, just viewed from the perspective of time rather than frequency. Frequency and time are intimately connected. A higher frequency corresponds to faster oscillations, which means a clock based on those oscillations ticks faster. A lower frequency means slower oscillations and a slower clock. The GPS satellite clocks, being higher in Earth's gravitational field, where spacetime is less curved, tick slightly faster than identical clocks on the ground. The difference is small, about 45 millionths of a second per day, due to gravity alone. There is also a competing effect from special relativity, because the satellites are moving at high speed, which slows their clocks down by about 7 millionths of a second per day. The net effect is that the satellite clocks gain about 38 millionths of a second per day compared to ground clocks. 38 millionths of a second might sound insignificant, but light travels about 11.4 kilometers in 38 millionths of a second. If GPS did not account for gravitational time dilation, your navigation would accumulate errors of roughly 10 kilometers per day. Within a week, your GPS would be off by tens of kilometers. It would be completely useless. The fact that GPS works, that it guides you accurately to within a few meters, is direct, practical confirmation that gravity affects the rate at which time passes, which is the same phenomenon as gravitational redshift applied to the ticking of clocks instead of the oscillation of photon frequencies. Every time you follow GPS directions to a destination and arrive where you expected, you are confirming Einstein's general relativity. Now let us consider what happens in more extreme gravitational environments, where the effects become far more dramatic than anything we experience on Earth. Neutron stars are the collapsed remnants of massive stars that have exhausted their nuclear fuel and exploded as supernovae. What remains is an object containing roughly 1.5 to 2 times the mass of our Sun, compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. The gravitational field at the surface is about 200 billion times stronger than at Earth's surface. In such an intense gravitational environment, gravitational redshift becomes dramatic. A photon emitted from the surface of a typical neutron star and observed by a distant astronomer would lose roughly 20 to 30% of its energy to gravitational redshift during its climb away from the surface. The frequency would drop measurably. A photon emitted as an X-ray might arrive at a distant telescope shifted noticeably toward lower frequencies, and the photon would still be traveling at exactly the speed of light. It would have lost a substantial fraction of its energy entirely through a decrease in frequency, without slowing down by even the smallest amount. Astronomers observe this regularly. When they study the X-ray emission from neutron star surfaces, the spectral lines, those fingerprint frequencies characteristic of specific elements, appear shifted to lower frequencies compared to laboratory measurements of the same elements on Earth. The shift matches the predictions of general relativity with high precision. This is gravitational redshift in action, observed across light years of distance, confirming that gravity changes the frequency of light without changing its speed. But neutron stars, as extreme as they are not the most extreme gravitational environments in the universe. That distinction belongs to black holes. And near a black hole, gravitational redshift reaches its ultimate expression. A black hole forms when matter is compressed so densely that the gravitational field becomes overwhelming. The curvature of space-time becomes so extreme that nothing, not matter, not light, not information of any kind, can escape from within a certain boundary. That boundary is called the event horizon, sometimes described as the Schwarzschild radius, after the physicist Karl Schwarzschild, who first calculated its size using Einstein's equations in 1916. The event horizon is not a physical surface. It is not a wall or a membrane. It is a mathematical boundary in space-time, beyond which escape is impossible. If you fell past the event horizon of a black hole, you would not necessarily notice anything unusual at the moment of crossing. Space would not look different. Time would not feel different. But from that point on, every possible path through space-time, every direction you could travel, would lead deeper into the black hole. The geometry of space-time inside the event horizon is configured so that moving forward in time inevitably means moving closer to the center. Escaping from inside the event horizon would require traveling faster than light, which is impossible. Now consider what happens to a photon emitted very close to the event horizon of a black hole, but still outside it. The photon climbs outward through the most intensely curved space-time in the universe. As it does, it is gravitationally redshifted to an extraordinary degree. A photon emitted just above the event horizon might lose 99% of its energy climbing away from the black hole, or 99.9%, or even more. The closer to the event horizon the photon begins its journey, the more extreme the redshift. At the event horizon itself, the gravitational redshift becomes infinite. A photon emitted precisely at the event horizon would be redshifted to zero frequency. Its energy would drop to zero. Its wavelength would stretch to infinity. For a distant observer, this photon would never arrive. It would be stretched out of existence, its frequency driven to nothing by the infinite curvature of space-time at the horizon. This is why nothing escapes from inside a black hole. Not because there is a physical barrier, but because space-time is so severely curved that any outward-directed photon is redshifted to zero energy before it can reach a distant observer. The photon is still traveling at the speed of light. It has not slowed down, but its frequency has been driven to zero by the geometry of space-time, and a photon with zero frequency carries zero energy. It has, in a very real sense, been erased by gravity. This is gravitational redshift taken to its absolute limit, and it demonstrates, in the most dramatic way possible, that photon energy is entirely a property of frequency. Gravity does not slow the photon. Gravity does not grab the photon and wrestle it to a halt. Gravity curves space-time, and the curvature changes the measured frequency. That is all.
But that is enough to drain every last quantum of energy from a photon, while leaving its speed completely untouched. The supermassive black hole at the center of our own galaxy, Sagittarius E star, has a mass of about 4 million times the mass of our Sun. Astronomers have observed stars orbiting this black hole at tremendous speeds, some reaching several % of the speed of light at their closest approach. They have measured the gravitational redshift of light emitted by these stars as they dip deep into the black hole's gravitational well and then climb back out. The results match general relativity precisely. The light from a star near Sagittarius E star is measurably redshifted when the star is close to the black hole, and less redshifted when the star is farther away. Frequency changes, energy changes, speed stays locked. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87, which has a mass about 6.5 billion times the mass of our Sun. The glowing ring of light surrounding the shadow is material orbiting the black hole at extreme speeds, emitting radiation that is being dramatically affected by the intense gravitational field. Photons climbing out of that gravitational environment are severely redshifted on one side of the ring and blue-shifted on the other, depending on the geometry and the relative motion of the emitting material. The interplay of gravitational redshift, gravitational blue shift, and relativistic Doppler effects creates the asymmetric appearance of the ring. All of this, every feature of that historic image, is consistent with photons that travel at a fixed speed and change energy solely through changes in frequency. Before we move on, let us pause to note that gravitational redshift has an exact counterpart, gravitational blue shift. When a photon falls into a gravitational well, instead of climbing out of one, the opposite happens. its frequency increases, its wavelength shortens, its energy rises. The photon gains energy by falling deeper into curved spacetime. You can observe this with the Pound-Rebka experiment run in reverse. Gamma rays directed downward in the Jefferson Tower, falling deeper into Earth's gravitational field, arrived at the lower detector with a slightly higher frequency than they had when emitted. They gained energy. They were blue-shifted, and once again, their speed did not change. It remained exactly the speed of light. Blue shift and red shift are mirror images of each other, and both reinforce the same principle. Photon energy is a function of frequency, not speed. Gravity changes frequency. It does not change speed. Cosmic rays from deep space, photons from distant sources falling into the gravitational well of a star or a galaxy cluster, all experience gravitational blue shift, gaining energy as they descend. When photons from the cosmic microwave background pass through a massive galaxy cluster, they gain energy falling into the cluster's gravitational well and lose energy climbing out the other side. If the universe were not expanding, these effects would cancel perfectly. The photon would gain on the way in exactly what it loses on the way out and emerge unchanged. But because the universe is expanding, the gravitational well is slightly shallower by the time the photon exits than it was when the photon entered. The photon comes out with a tiny net energy gain. This effect, called the integrated Sachs-Wolfe effect, has been detected in careful observations of the cosmic microwave background. It is a subtle but real demonstration that gravity, expansion, and photon frequency are all connected, all playing out against the backdrop of a constant, invariant speed of light. What gravitational redshift ultimately reveals is something extraordinary about the nature of energy, time, and space-time. The fact that a photon loses energy climbing out of a gravitational well is not a mechanical process. Nothing collides with the photon. Nothing absorbs part of its energy. No force, in the classical sense, acts upon it. Instead, the structure of space-time itself, the geometry of the universe in the vicinity of a massive object, determines how frequency is measured at different locations. Time passes at different rates at different heights in a gravitational field. Lower in the field, time passes more slowly. Higher in the field, time passes more quickly. A photon emitted at one rate of time and received at a different rate of time will be measured at a different frequency, because frequency is oscillations per unit of time, and the unit of time itself has changed between emission and reception. This is perhaps the most profound aspect of gravitational redshift. The photon does not change in any absolute sense. If you could somehow ride alongside the photon, which you cannot because no massive observer can travel at the speed of light, you would not detect any change. The photon does not feel itself losing energy. It does not experience a gradual weakening. What changes is the relationship between the photon and the observer. The curvature of space-time means that clocks at different locations tick at different rates. A photon with a specific number of oscillations per second, as measured by a clock at one location, will have a different number of oscillations per second, as measured by a clock at another location, simply because the clocks are running at different rates. The photon is the same. The measurement changes because space-time itself is curved. This makes gravitational redshift fundamentally different from the energy loss of a thrown ball. When you throw a ball upward and it slows down, the ball is genuinely, physically losing kinetic energy. If you could ride alongside the ball, you would see it decelerating relative to you. The ball's change is absolute and measurable from any reference frame. Gravitational redshift is different. It is a relational effect, arising from the curvature of space-time and the differing flow of time at different locations. It is no less real. The energy received by the distant observer is genuinely lower. The photon genuinely arrives with less energy.
but the mechanism is geometric rather than mechanical. It is spacetime telling different clocks to run at different rates, and frequency, being measured in oscillations per tick of those clocks, changes accordingly. Gravity can take energy from light. Gravity can give energy to light. And in both cases, speed is untouched. The photon is indifferent to gravity in terms of velocity. It always moves at the speed of light. But gravity reshapes the oscillation, the heartbeat of the photon, stretching or compressing it by curving the spacetime through which the photon travels. This is one of the most beautiful consequences of general relativity, and it demonstrates with extraordinary clarity that photon energy is not about speed. It is about frequency, always frequency. But gravity is not the only force in the universe capable of reshaping a photon's frequency across vast distances. There is another mechanism operating on the largest scales imaginable that has drained energy from photons for billions of years. A mechanism that does not involve any massive object, any gravitational field, any relative motion between source and observer. A mechanism woven into the very expansion of the cosmos itself. There is one more way the universe can drain energy from light without touching its speed, and it operates on the largest scale imaginable. Not the scale of a laboratory tower, not the scale of a star or a black hole, the scale of the entire cosmos. This is cosmological redshift, and it is, in many ways, the grandest demonstration of how photon energy can change while photon speed remains perfectly, immovably fixed. To understand cosmological redshift, you first need to understand something extraordinary about the universe itself. Something that was not discovered until the 20th century, and that still strikes many people as deeply counterintuitive when they first encounter it. The universe is expanding. Not in the sense that galaxies are flying outward through space like shrapnel from an explosion, although that is how most people picture it. The expansion is something stranger and more profound than that. Space itself is stretching. The fabric of the universe, the actual distance between objects that are not bound together by gravity or other forces, is increasing over time. New space is being created between distant objects, pushing them farther apart without either object moving through space in the traditional sense. This distinction matters enormously for understanding cosmological redshift, so let us be very careful with it. When a fire truck drives away from you with its siren blaring, the sound waves reaching your ears are stretched because the truck is physically moving through the air, putting more distance between itself and each successive wave crest. This is a Doppler shift. The source is moving through the medium. The waves are stretched by that motion. The same thing happens with light. If a galaxy is moving away from you through space, the light it emits is Doppler redshifted. The galaxy's motion through space stretches the wavelengths. Cosmological redshift is different. In cosmological redshift, the galaxy is not moving through space in any significant way. The galaxy is essentially sitting still in its local region of space, but the space between you and that galaxy is expanding. New distance is being added between you and the galaxy, not because either of you is traveling, but because the fabric of space itself is stretching. And as space stretches, it stretches everything in it, including the wavelengths of photons traveling through that space. Think of it this way. Imagine drawing two dots on the surface of a balloon, then drawing a wave pattern between them with regular peaks and valleys. Now inflate the balloon. The two dots move farther apart, but the wave pattern also stretches. The peaks spread out. The distance between successive crests increases. The wavelength gets longer. This happens not because anyone is pulling the wave or pushing the dots. It happens because the surface itself is expanding, carrying the dots and the wave along with it. Photons crossing the expanding universe experience exactly this. A photon is emitted by a distant galaxy with a certain frequency, a certain wavelength. The photon begins its journey across intergalactic space, traveling at the speed of light. While the photon is in transit, space expands.
The wavelength of the photon, which is a physical length embedded in the fabric of space, gets stretched along with everything else. By the time the photon arrives at a telescope on Earth, its wavelength is longer than it was when it was emitted. Longer wavelength means lower frequency. Lower frequency means less energy. The photon has been cosmologically redshifted. It has lost energy. And it has done so without slowing down by even the smallest fraction. The photon did not use up energy to maintain its speed. Nothing collided with the photon to drain its energy. No force acted on the photon to slow its oscillation. The expansion of space itself, the stretching of the very arena through which the photon travelled, lengthened its wavelength and decreased its frequency. The photon was a passive passenger on an expanding surface, and the expansion altered its properties without any mechanical interaction whatsoever. This is fundamentally different from Doppler redshift, even though both result in lower measured frequency. Doppler redshift involves relative motion through space. Cosmological redshift involves the expansion of space itself. The distinction is physically real and leads to measurably different predictions about the relationship between distance, velocity, and redshift at very large scales. The discovery that the universe is expanding is one of the most important scientific findings in human history. The story begins in the 1920s. The American astronomer Vesto Slipher had been measuring the spectra of what were then called spiral nebulae, fuzzy, spiral-shaped smudges of light in the sky whose true nature was not yet understood. Slipher found that nearly all of these nebulae showed redshifted spectral lines. Their light had been shifted to lower frequencies. This suggested they were moving away from us, but the reason was unclear. In 1929, Edwin Hubble combined Slipher's redshift data with his own distance measurements and discovered something remarkable. The farther away a galaxy was, the greater its redshift, and the relationship was proportional. A galaxy twice as far away was receding twice as fast. 3 times as far, 3 times as fast. This was not the behavior of objects flying apart from a single explosion. In an explosion, the fastest fragments travel the farthest, but the relationship between speed and distance is not as clean and universal as what Hubble observed. Instead, it was exactly the pattern you would expect if space itself were uniformly expanding. Every point in space is moving away from every other point. The more space there is between two objects, the more total expansion occurs between them, and the faster they appear to recede from each other. The Belgian physicist Georges Lemaitre had actually predicted this expansion theoretically a few years earlier, deriving it from Einstein's equations of general relativity. Einstein himself had initially resisted the idea, adding a term to his equations specifically to prevent them from predicting an expanding universe, because he believed the universe should be static. He later called this his greatest blunder, when the expansion was confirmed observationally. Today, the expansion of the universe is one of the best established facts in all of science. It has been confirmed by multiple independent lines of evidence. The redshift-distance relationship that Hubble discovered has been extended to galaxies billions of light-years away. The predictions of Big Bang cosmology, which is built on the expanding universe model, have been verified with extraordinary precision. And the most dramatic piece of evidence, the one that concerns us most directly tonight, is the cosmic microwave background. The cosmic microwave background is the afterglow of the Big Bang itself. It is the oldest light in the universe, released when the cosmos was only about 380,000 years old. At that time, the universe was a hot, dense plasma of particles and radiation. Photons could not travel freely because they were constantly being absorbed and re-emitted by the charged particles in the plasma. The universe was opaque, filled with a blindingly bright fog of light and matter. Then, as the universe expanded and cooled, something critical happened. The temperature dropped below about 3000 degrees Kelvin. At this temperature, electrons could finally combine with protons to form neutral hydrogen atoms. Neutral atoms do not scatter photons the way free charged particles do. The universe suddenly became transparent. Light that had been trapped in the plasma was released, free to travel through space for the first time. This moment is called recombination, and the light released during recombination has been traveling through space ever since. At the moment of release, roughly 13.8 billion years ago, this radiation had the spectrum of a hot, glowing object at about 3000 degrees Kelvin. It was intensely energetic. Its peak frequency was in the near-infrared range, close to visible light. If you could have been there, the universe would have glowed a deep, warm orange red in every direction. But you were not seeing that warm glow tonight. You were not bathed in near-infrared radiation from the early universe. Instead, this ancient light, this primordial radiation released when the universe was less than 400,000 years old, now fills the cosmos as faint, cold, microwave radiation with a temperature of only about 2.725 degrees above absolute zero. What happened? The universe expanded. For over 13 billion years, space has been stretching, and the wavelengths of those ancient photons have been stretching along with it. Radiation that began with wavelengths in the near-infrared, just beyond the red end of the visible spectrum, has been stretched by the expansion of space by a factor of more than 1,000. Its wavelength is now over 1,000 times longer than when it was emitted. Its frequency is over 1,000 times lower. Its energy per photon is over 1,000 times less. The once blazing glow of the young universe has been redshifted into faint, cold microwave radiation barely above the temperature of absolute zero. This is cosmological redshift, operating over the largest possible distances and the longest possible timescales. Photons that have been traveling for over 13 billion years, crossing an expanding universe, losing energy continuously as their wavelengths are stretched by the relentless expansion of space. And through all of that, through every single one of those 13 billion years, every one of those photons has been traveling at exactly the speed of light. Not one of them has slowed down. Not by a meter per second. Not by a millimeter per second. Their energies have dropped by a factor of more than 1,000, and their speed has remained absolutely, perfectly constant. The cosmic microwave background was detected accidentally in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey. They were testing a sensitive antenna designed for satellite communication and found a persistent, faint hiss of microwave radiation coming from every direction in the sky. No matter which way they pointed the antenna, the signal was the same. They checked for equipment problems. They cleaned pigeon droppings from the antenna. They accounted for every possible source of interference. The hiss remained. Eventually, they learned that a group of physicists at nearby Princeton University had predicted exactly such a signal as a relic of the Big Bang. Penzias and Wilson had accidentally discovered the oldest light in the universe. They received the Nobel Prize for it in 1978. Since then, the cosmic microwave background has been studied with increasingly precise instruments. The COBE satellite, launched in 1989, confirmed that the radiation has a perfect thermal spectrum, corresponding to a temperature of about 2.725 degrees above absolute zero. The WMAP satellite, launched in 2001, mapped tiny temperature variations across the sky with unprecedented precision. These variations, only about 1 part in 100,000, are the seeds of all the structure in the universe today. Slightly denser regions in the early universe eventually collapsed under gravity to form galaxies, stars, and planets. The pattern of hot and cold spots in the cosmic microwave background is a snapshot of the universe when it was less than 400,000 years old, preserved in light that has been travelling and redshifting ever since. This ancient radiation is the most compelling evidence that photons can lose enormous amounts of energy without slowing down. These photons have lost more than 99.9% of the energy they carried when they were first released. They began as vigorous near-infrared oscillations and have been stretched into languid microwaves. Yet they are still moving at the speed of light. They have not tired. They have not faded from exhaustion. They have not consumed their energy as fuel. They have simply had their wavelengths stretched by the expansion of space over 13 billion years of travel. Frequency down, energy down, speed unchanged. This is the right place to address an idea that was once proposed as an alternative explanation for cosmological redshift. It is called the tired light hypothesis, and it is wrong. But understanding why it is wrong reinforces everything we have discussed. The tired light hypothesis was proposed by Fritz Zwicky in 1929. Zwicky suggested that photons might lose energy gradually as they travel through space, not because space is expanding, but because of some unknown interaction that slowly drains their energy over enormous distances. In this picture, the universe would not need to be expanding at all. The redshift of distant galaxies would simply be the result of photons getting tired over their long journeys, losing energy through some friction-like process in the vacuum. The idea has a certain intuitive appeal. It feels natural to imagine light getting weaker over long distances, fading like the sound of a distant voice. And it avoided the startling conclusion that the universe is expanding, which many scientists at the time found difficult to accept. But tired light fails on multiple fronts. First, if photons were losing energy through some scattering or absorption process as they travelled, the images of distant galaxies should appear blurred. Scattering spreads light out, smearing images. But distant galaxies observed with powerful telescopes are sharp and well resolved, not blurred. Second, tired light cannot explain the specific relationship between redshift and distance that Hubble observed. The expansion of space produces a particular mathematical signature in the redshift-distance relation, especially at very large distances, that tired light does not reproduce. Third, tired light predicts a specific pattern for how the brightness of distant supernovae should vary with distance, and the observed pattern does not match. The observations match the expanding universe model instead. Fourth, and most decisively, tired light cannot explain the cosmic microwave background. The perfect thermal spectrum of the cosmic microwave background is exactly what you expect from radiation released by a hot plasma and then redshifted by the expansion of space over billions of years. Tired light has no mechanism to produce a perfect thermal spectrum filling the entire sky uniformly. Most importantly for our discussion, the tired light hypothesis treats photon energy as fuel spent during travel. We addressed this exact misconception when we cleared away common misunderstandings earlier. A photon does not burn through reserves to sustain its speed. That point is firmly established. What tired light adds is a proposed mechanism for the redshift of distant galaxies, and that mechanism fails every observational test. Beyond the 4 failures just described, there is a fifth. The expanding universe model predicts that events in distant galaxies should appear to unfold in slow motion, their timescales stretched by the same factor as their light. This cosmological time dilation has been directly observed in the light curves of distant supernovae. They fade more slowly than nearby supernovae by precisely the amount the expanding universe predicts. Tired light predicts no such time dilation. The evidence is decisive. Photons lose energy through specific, identifiable, well-understood physical mechanisms. Doppler redshift due to relative motion between source and observer. Gravitational redshift due to the curvature of spacetime near massive objects. Cosmological redshift
due to the expansion of space over large distances.
Each of these mechanisms changes the photon's frequency without altering its speed. None of them involves the photon using energy as fuel. None of them involves friction or fatigue. The tired light hypothesis is not just unsupported by evidence. It is based on a fundamental misunderstanding of how massless particles behave. Now, let us bring everything together. We have travelled a long road, from the intuitive physics of thrown balls to the quantum nature of photon energy, from laboratory measurements of gravitational redshift in a university tower to the ancient light of the cosmic microwave background crossing an expanding universe for over 13 billion years. And every piece of this story has pointed toward the same conclusion. The paradox we began with was an illusion. It seemed paradoxical that light could lose energy without slowing down, only because we were applying the wrong framework. We were using the rules of massive objects, rules where energy is stored in the relationship between mass and speed, and trying to force those rules onto something that has no mass at all. When you remove mass from the picture, the connection between energy and speed dissolves. It does not weaken, it vanishes entirely. For a massless particle, energy and speed are independent properties, governed by independent aspects of physics. A photon's speed in vacuum is fixed at 299,792 kilometers per second. This speed is not maintained by effort or fueled by energy reserves. It is a structural constant of spacetime, a consequence of how space, time, and electromagnetism are woven together in the fabric of reality. It is the speed at which causality itself propagates, the speed at which information can travel through spacetime. It is built into the geometry of the universe at the deepest level, and no physical process can alter it for a massless particle in vacuum. A photon's energy is carried by its frequency. High frequency means high energy. Low frequency means low energy. This relationship, energy equals Planck's constant times frequency, was discovered at the turn of the 20th century and has been confirmed by over 100 years of experiments, observations, and practical applications. It is as solidly established as any relationship in physics. When a photon loses energy, its frequency decreases and its wavelength lengthens. This is redshift. When a photon gains energy, its frequency increases and its wavelength shortens. This is blueshift. In both cases, the speed of the photon in vacuum remains exactly constant. The energy change is encoded entirely in the change of frequency. Speed is untouched. Speed is always untouched. The universe provides multiple mechanisms for shifting a photon's frequency. Relative motion between source and observer produces Doppler redshift or blueshift. The curvature of spacetime near massive objects produces gravitational redshift or blueshift. The expansion of space over cosmological distances produces cosmological redshift. Each mechanism changes frequency. None changes speed. Each drains or adds energy. None accelerates or decelerates. This is not a failure of energy conservation. Energy is conserved in every individual case, once you account for the full picture. In Doppler shifts, the energy difference is accounted for by the relative motion of the source and observer. In gravitational redshift, the energy change is tied to the structure of spacetime and the relationship between time flow at different locations in a gravitational field. In cosmological redshift, the question of energy conservation becomes more subtle because the expansion of space itself complicates how energy is defined over cosmological distances and timescales. But in no case does energy simply vanish into nothing. The physics is consistent. The bookkeeping works. It just requires abandoning the intuition that energy must always manifest as speed. What we have learnt tonight is something deeper than a fact about photons. We have learnt that our intuitions, however reliable they are in the world of everyday objects, can fail spectacularly when applied to the extremes of nature.
The universe is not obligated to behave the way our experience tells us it should. Balls slow down when they lose energy because balls have mass and their energy is stored in their velocity. Photons do not slow down when they lose energy because photons have no mass and their energy is stored in their frequency. Both statements are true. Both are consistent with the laws of physics. They simply describe different categories of existence governed by different rules. The next time you see sunlight warming the ground, know that each of those photons left the surface of our star 8 minutes and 20 seconds ago, travelling at the speed of light. Some of those photons have been gravitationally redshifted ever so slightly during their climb away from the solar surface, losing a tiny fraction of their energy to the sun's gravitational field. They arrive with marginally less energy than they had when they were emitted, but they arrive at exactly the same speed they left with. The next time you look at a distant star on a clear night, know that the photons entering your eyes have been travelling for years, possibly decades, possibly centuries. They have crossed vast stretches of space at the speed of light, and they arrive carrying exactly the energy that their frequency encodes. If that star is moving away from us through space, the photons are Doppler redshifted, carrying slightly less energy than they had at emission. But their speed has not changed. And somewhere out there, in every direction you look, ancient photons from the cosmic microwave background are arriving at Earth right now. Photons that have been travelling for over 13 billion years. Photons that began as energetic near-infrared radiation in a young, hot, glowing universe, and have been stretched by the expansion of space into faint microwaves barely above absolute zero. These photons have lost more than 99.9% of the energy they started with. They are among the most redshifted photons in the observable universe, and they are travelling at exactly the speed of light. The same speed they have always travelled. The same speed every photon in the history of existence has travelled. They have not slowed down, they have not gotten tired. They have not spent their energy as fuel to maintain their journey across the cosmos. They have simply had their frequency reduced by the stretching of space, and they carry less energy because of it. Their speed remains what it has always been, and what it will always be. A constant, an invariant, a fundamental truth about the universe that does not bend, does not break, and does not make exceptions. Light can lose energy without slowing down because energy and speed are not the same thing for a photon. They never were. They never will be. For objects with mass, energy and speed are bound together, and losing one means losing the other. For massless particles travelling through the vacuum at the one speed the universe permits them to travel, energy lives somewhere else entirely. It lives in the rhythm of the oscillation, in the frequency of the wave, in the heartbeat of the electromagnetic field. Change the heartbeat and you change the energy. But the photon keeps moving, always at the same speed, from the moment it is born to the moment it is absorbed, across a laboratory or across the observable universe, through flat space-time or through the most extreme curvature near a black hole, through a static cosmos or through a universe expanding for billions of years. The speed of light does not negotiate, it does not compromise, it does not yield. It is woven into the structure of reality itself. And that is how light can lose energy without slowing down.